So hello and welcome student to today's lecture, and this is course number MA412 linear algebra, and today we are going to learn lecture number 29. Okay. Yeah. So today we'll learn a new concept of new type of operators, and so what is our motivation? So our motivation is that, so you recall that if we have a vector space with say dimension finite, then and obviously linear operators on V, then V has a basis B consists of eigenvector consisting of eigenvectors of T. This is if only T is diagonalizable, right? Diagonalizable. And you can ask similar type of question for inner product space, that whether the inner product space has a basis consisting of eigenvectors which is also orthonormal. So what does that mean? That means whether we have a orthonormal basis consisting of eigenvector of a linear operator. Okay, under what condition? So this is our goal to understand, and with this goal we just first try to understand some of the properties of adjoint operators that we have learned in last lecture. Okay, so we'll start with this proposition. Okay, the first proposition. So that tells you that if you have a finite dimensional inner product space and some linear operator which has an eigenvector, then the adjoint operator is also has eigenvector. Okay, so let V be a finite dimensional inner product space and linear operator you choose on LV. Okay, so if T has an eigenvector then T star has also, so that means T star also has eigenvector. Okay. Okay, so how do we prove this kind of theorem? That whenever, so the adjoint, we define that adjoint of a linear operator exists for finite vector space, sorry, inner product space. Okay, and there exists an adjoint guaranteed from Ridge representation, right? And so now let us give a proof for this statement. Proof. So this is given that T has eigenvector. So let so V belongs to V, B, and eigenvector vector of eigenvector of T corresponding to eigenvalues. What is corresponding to the eigenvalue, say C. Okay, C be inside the field. A field can be complex or real, doesn't matter. Okay, and then what does that mean? That means T of V equal to C of V. Okay, for this. Okay, now if T of V equal to CV, so what does that mean? That means T minus Ci of B. This is 0, right? This is 0 vector. Okay, and hence so thus what you can do, so you can take an product of T minus I with V with any other vector inside V. So you choose any other vector, say U belongs to V. This is 0, this is true for all U belongs to V for any vector, because this is 0 vector. So if you take a product with 0 vector with any vector, that has to be 0, right? But then you know that you can use the property of adjoint operator that tells you that V this becomes T minus Ci whole adjoint with U, that is 0. This for all U belongs to V, right? So what does that mean? So okay, so you also say here we note that this V cannot be 0 because V is eigenvector, right? So what does this mean? This means that P comma T star, and this means that C I star equal to I, right? But Ci whole star equal to C by into I. That property we already learned in last class, that with U this is 0, right? This is also true for all B belongs to V. So what does that mean? That means these vectors are inside the range of the operator T star minus C bar I, right? Because you are running all the U belongs to V, so this vector belongs to the range of this, right? So what does that mean? That means your original eigenvector V of T is actually now is orthogonal to the range of this operator, right? So thus V is orthogonal to this range of T star minus C bar of I, right? That is, I can write down. I will write down this perpendicular to range of T star minus C bar of I. Okay. So you have a so what does that mean? That means range of the operator. So range of operator has a non-zero vector which is orthogonal to the range, right? So what does that mean? That means this implies that range of this operator is not equal to V itself, right? So you have a something which is orthogonal means is outside this non-zero vector, the non-zero vector which is orthogonal to this. So the range cannot be full thing. So what does that mean? That means the operator T star minus C bar I is not onto, right? The range is not the full space, means it's not subjective. Subjective means onto, and hence it is not injective, right? Because on finite dimensional vector space, surjectivity is equivalent to injectivity, and hence it is not injective. So you have operator which is not injective operator. So this implies that the null space of that operator T star minus C bar I it is not trivial. This is not trivial. So 0 obviously always belongs to null space of any operator, but because this is not 1 and that means the null space contains more than one vector, right? So thus there exists a non-zero vector, there exists some fetus which is non-zero vector, belongs to the null space and belongs to the null space of this t star minus c bar I, and hence hence t star v dash equal to c bar v dash, and hence v dash is an eigenvector of t star. So what does that mean? That means if the origin operator has eigenvector, then the adjoint operator is also an eigenvector, right? And it's true for any finite dimensional vector space or another inner product space. Okay, so this proof guarantees that the existence of eigenvectors from T to T star. Okay. Now the next theorem is very important theorems we need to solve, and that tells you that the sufficient condition for something called triangulation of a linear operator on the linear product space, right? And this for the vector space, obviously, if you don't have inner product, then we can have results, but for inner product space also we can have a better results, and this is called Schur's theorem. So let me define this. Schur's theorem. What does Schur's theorem tells you? That suppose we have a so let be a finite dimensional inner product space, inner product space, and you have linear operator say T belongs to LV, the linear operator on V. Okay. So if this characteristic polynomial of T, if the characteristic polynomial of T splits means split over the field. Okay, split over the field F. Then what happens? Then V has an orthogonal basis. This is very important. Or there is an orthogonal basis, whatever. V has an orthogonal basis. Orthonormal basis B such that what happens? Such that the matrix representation of T with respect to this basis is upper triangular. Upper triangular matrix or upper triangular. Okay, so what does that tell you? It tells you that if characteristic polynomial split is actually gives you a sufficient condition for existence of orthonormal basis, which represents that matrix as an upper triangular matrix. Okay, and the proof is not straightforward. We need to understand the proof properly, and we will do something called mathematical induction. That method of this mathematical induction we have done many times here also. Okay, so the proof. So we will use mathematical induction. On the dimension, okay, dimension of V, whatever. So if the dimension of if it is one, then if this dimension of v equal to one, then this is obviously everything trivial, right? We, there is only one dimensional thing, right? So uh, then there is nothing to prove. Nothing to prove. Nothing to prove. Okay. Now, so I will assume that. So what will be inverse hypothesis? So now I assume that the statement is true. The above statement, okay, statement is true for what? For all linear operators, or any or whatever, any linear operators, linear operator on say so let me assume that in my own dimension. So maybe I can say this is dimension operator of say n minus 1 dimensional inner product space, okay, um, inner product space with what condition? Whose characters is polynomial, so is actually split, right? Whose character is polynomial. So the any linear operator on this whose character is polynomial, whose characteristics is big polynomial splits. Polynomial splits. Okay, so in this case we are going to give a proof. Okay. So now assume that now let dimension of v equal to say n, and yeah, so and t or this characteristic polynomial of t, characteristic polynomial of t split over f, okay. So then obviously what does that mean? T split means t has eigenvalues and eigenvectors, so t has eigenvectors vectors, and so does t star. So t star also has eigenvector, right? So now with the loss of generality, I am assuming that t star has eigenvector with norm 1. That is obvious because if you have eigenvector, then you can divide it by the norm of that vector, and then so now without loss of generality, assume that so we have eigenvector z, so z b and eigenvector of t star with norm 1. Okay, so it is possible, because if not, then what you can do is though, so if say t star of z equal to something, say cz, then you can divide it by norm, right, both sides. Now see, the new vector has a norm 1, right? So you can always do it. Okay, so suppose norm 1 corresponding to eigenvectors, eigenvalues corresponding to eigenvalue, so C. Okay, and I am assuming that this is norm 1 means a unit vector, right? Okay, so now what we will do, so we will choose a subspace. So let W be the subspace which is spanned by this eigenvector. So eigenvector Z, and you are taking this one dimensional subspace spanned by this Z. Okay, so this is eigenvector of T star, remember, and W, this is obviously then is inside V, right? One dimensional subspace of V, right? Now what is my claim? My claim is that because V is 5-dimensional, so W power exists, and this W power, which is this orthogonal complement of W, is T invariant. This is my claim. Okay, so W, obviously W is T star invariant, and if W is T star invariant, then W power is T invariant. This is the claim. Okay, so how to prove that? So so to prove something T invariant, what do you need to prove? You need to prove that every element of W power, the image under T is again element of W power. So what does that mean? That means then let something, you choose any element, say Y belongs to W power, and then what do we need to show? We need to show that dy is also element of W power, right? Then W power will do T invariant. Now to show ty is element of W power, so what I need to show? So ty is orthogonal to W, right? And W is generated by only one element. So this is the basis actually of W. So it is better to show for the basis element, right? So then what you should do? So you start with the inner product of ty with z, and we will show that this inner product is 0 actually, and that will prove that ty is orthogonal to W, and hence ty belongs to W power. But this is nothing but y into T star of z. But we know that see, z is the eigenvector of T star with eigenvalue T C. So what does that mean? That means this is nothing but y comma cz, right? Because z is eigenvectors of T star. So this is it. Now see, the property number tells you that this will be nothing but C bar of this y comma z, right? But what was y? So y is inside W power, so y is orthogonal to z, and hence this vector is 0. So it is nothing but C bar into 0, which is equal to 0. So what does that mean? That means that ty is actually orthogonal to W power, whatever we just claimed. Okay, so this proves that W power is T invariant, and once if we have something T invariant, then you can restrict the operator on the invariant subspace to get another restricted linear operator, right? Now let so this TW power is the restriction of T, and this map from W power to W power, right, is the restriction operator. Restriction of T on W power. Okay, so you restrict and you have another operator on W power. But the thing is that W power is no longer the full vector space, right? Because W is one dimensional, and we know that dimension of W plus dimension of W power is nothing but dimension of V, which is nothing but n, and this is one dimensional, so W dimension of W power is actually n minus 1 dimension, right? Okay, now because the characteristic polynomial of the restriction actually divides the whole characteristic polynomial that we proved long back ago. So as uh, TW pub, or rather I should say characteristic polynomial as the characteristic polynomial poly of polynomial means characteristic polynomial of TW pub divides this characteristic polynomial of T, then this also the characteristic polynomial of TW pub is also split, right? Because original was splitting. Original is product of distinct linear factors, and it is a divisor of that, so it has to be sorry, not distinct, product of linear factor. There has to be also product of linear factor. So right, then characteristic polynomial of TW pub also split, right? Splits over F, same vector space. Okay, so now we have a vector in a product space of dimension n-1 who and the linear operator TW pub on the W pub whose characteristic polynomial split. So you can use the now induction, right? Thus the induction hypothesis tells you, I mean, thus by the induction basis there exists a basis, something say beta 1 basis of another orthogonal basis. Okay, there exists an orthonormal basis say beta 1 of this W pub such that TW pub with respect to this basis B1 is upper triangular. Okay, so W pub is a subspace of V of dimension n-1 which has an orthogonal basis B1 such that the matrix representation of TW pub with respect to the basis is upper triangular. So now you can choose B. Your B is this B1 union Z. Now what is the advantage here? Advantage is that Z is orthogonal to W pub obviously, and B1, so there is the orthogonal to B1, and B1 has all the orthogonal vectors which are also unit, like norm is 1 and Z norm of there is also 1, so this is an orthonormal basis of V, right? And also that the matrix representation of T with respect to this basis B is upper triangle, right? Because till V, I mean till n-1 many vectors it is upper triangular, and the last vector has no other choice. It has to be if the last vector, if you write down linear combination of all the other vectors, still it is upper triangular, right? So it's upper triangular, doesn't matter. Triangular. Okay. Okay, so this is the proof actually. So that tells you that you have a basis of orthogonal vectors such that the matrix representation become upper triangular, and that is happening because T split. The characteristic polynomial split. Okay, because of that this is possible. Okay, so now whatever we discussed, we can easily understood that if I have a diagonal matrix or rather diagonal level operator Then what we can do, so we can always um, find out the orthogonal basis such that TB bar is diagonal, right? So that is obviously, see, this is coming from both the case that existence of basis with respect to which is orthogonal, and then now from the source theorem we can actually say that that basis you can make it orthogonal basis. Okay. So now, not only that, so if you have an operator which is diagonal, then the adjoint of the operator. So if say, so note that if T is diagonalizable. Okay, so you have a orthogonal basis such that this is a diagonal matrix, right? This is a diagonal matrix. Then this implies C, this star with respect to the same basis with what? So it will happen that nothing but that adjoint of the original matrix, right? But adjoint of diagonal matrix is also again diagonal, right? So is also diagonal matrix. Okay, so what does that mean? That means for diagonal matrix, the adjoint also diagonal, and then if you see that two diagonal matrix commutes, so both T and T star commutes, right? So this implies T commutes with T star, commutes with T star, and this observation actually for inspire us to define a new kind of operator, and these are called normal operators. So let us define it. Define definition. So let V be an inner product space okay, and we define, so we say a T belongs to LV is normal. It's very important, or rather normal operator if T commutes with T star. So that means if T star equal to T star T. Okay. And similarly for matrix, what will say? So matrix is normal matrix if A star equal to A star A. Okay. So T is normal means with respect to a, so there exists a basis with respect to orthogonal basis with respect to that, and the matrix representation they come to each other, right? Okay. So this definition, obviously there are many theorems and many properties we are going to learn, but before that let us give some example of this type of matrix. Okay. So okay, so example, obviously for example 1, if T is diagonalizable, okay, then T is normal, that whatever we discuss. Okay. Maybe example 2, so these rotation matrix are also normal matrix. What does that mean? So you choose a rotation matrix, two dimension rotation maybe, so it from R2 to R2. R2 is a inner product space on R2 with respect to standard inner product. Okay, so with standard inner product on R2 over R. Okay, so this is I'm assuming. So then with respect to that, and so this is I choose this. So this rotation by some angle, say some theta, which is in between 0 to pi. Okay. Then what will be the metric representation with respect to the basis, the standard inner product, and okay, so we'll let so B is so 1 0 0 1, the standard basis, whatever order basis. Okay, and so with respect to this basis, TB will be what? So TB will be nothing about cosine theta sine theta minus sine theta cosine theta. Okay, so this was that matrix. So let me write down this is a matrix, something say A. Okay, and then what will be A star? So A star will be nothing but okay, so cosine and then the sine, and so this is a real, so it doesn't matter, so right. Okay, so now now you check what happened to A star or A star A. In this case actually A star will be what? So if you multiply cos theta cos square theta plus sin square theta, which is 1, then cos sin theta minus sin theta is 0, so 0 1, so this is identity, right? And similarly it is true for A star A also, so they come together, right? Okay, so this is an example of normal matrix or normal operator. Okay, maybe another operator, let me define it. So if you have a skew symmetric matrices which is over real numbers, for example. Okay, so let A be a real skew symmetric matrix, that is A transpose equal to minus A, and then obviously A star equal to A transpose, right? So A star equal to A transpose, and you can see that A star A is equal to A star, which is nothing but minus A square, right? So real skew symmetric matrices are also a normal matrix. Okay, so there are plenty other examples. These are some important examples. Okay, so now whatever we learned, so we have learned that so if V has a orthogonal basis of eigenvectors of T, then actually the T becomes orthonormal. So that means, okay, so remark, so what we learn that let V be a finite dimensional inner product space over some field F. Okay, so if V has an orthonormal basis, say B, of eigenvectors of a linear operator T is linear operator, okay, and then T is diagonalizable, right? Because orthogonal basis or eigenvectors means diagonalizable, hence is normal, right? And T is normal. That means T star equal to T star T. Now one can ask, is that converse is true? So if you have a norm operator, then it has the basis, the inner product space V has a orthonormal basis of eigenvectors or not. Okay. The answer is not true in general if it is real vector space. But for complex vector space, this is true. We are going to prove it. Before that, we need some property, and let us try to. Or maybe we can give the proof first. It will be easier. Then we will come to the properties. Okay. So this statement is not true in general, because you see that even the operator is normal, it may not that the operator may not have eigenvector over real numbers, okay, and hence it may not have a basis vectors. It may not have orthonormal basis whose elements are eigenvectors actually of the linear operator. But for complex numbers, it is true, because complex number is algebraically closed field, and hence minimal polynomial of any linear operator, that's split actually, right? So you can use the Schur's theorem. Okay, so now let us give the proof of that. Okay, so what is the theorem then? Theorem. So let V be a finite dimensional complex inner product space. Complex inner product space, and you have a linear operator on V. Okay, then T is normal. This is true if and only if what happened, there exists a orthogonal basis. So if and only if there exists an orthonormal basis of V consisting of eigenvectors of eigenvectors of T. Okay. So this is if only condition, and obviously one part is simple. We just have this remark tells you, right? Because if we have a orthogonal basis whose elements are eigenvectors, then the operator is diagonalizable, and hence this is normal, right? But converse is not true in general unless it is a complex vector space. Okay. So now we need to prove only one part, that we have a linear operator which is normal on a complex things, and then we need to find the orthogonal basis, okay, whose elements are eigenvectors of T. Okay, so this is we need to only prove. So proof. So again we will do the obviously mathematical induction on this. So we will use induction on this dimension of v, which is n, right? Now for n equal to 1, so this everything is trivial, right? N equal to 1 is trivial always, and we can assume that it is true for any vector space of dimension n minus 1, right? Now so what will show, so let we assume that that T is normal operator. Okay, so then what happened? Okay, so because C is okay, so because V is a complex vector space as if equal to C, I am assuming A is equal to C here. This minimal, this characteristic polynomial of T, characteristic polynomial of T splits over C. That is true because of fundamental theorem of algebra, right? Every polynomial split over C. C is something called algebraically closed field. Okay, so that is true. And once so that is because of fundamental. Okay, so fundamental theorem of algebra. Let me write it down. Fundamental theorem of algebra. Okay, now if T is split and then you have a source theorem. Source theorem tells you that so thus by source theorem, so by source theorem there exists the basis B of this, so this is orthonormal, so orthonormal basis, orthonormal basis of V such that what happens, such that this T with respect to B is upper triangular, right? So theorem tells you that. So what does that mean? That means obviously, so this means upper triangle means that T of V1 equal to this A11. So let me write down, this is a matrix say A, which is Aij. Okay, so A11 into V1, right? First one. So that is obvious that V1 is an eigenvector of T. This is obvious, right? Now in the hypothesis I am assuming, so I assume in the hypothesis, that means I am assuming that till n minus 1 these are all true. So so by induction hypothesis, by induction hypothesis assume this B1 B2 up to Bn minus 1 so I am assuming that these all are actually they are eigenvectors of T. Okay, with corresponding to eigenvalue with maybe eigenvalue maybe C1, C2 and Cn minus 1, something like that. So C1 is equal to A11 here. Okay, and this A11 is nothing but C1. Okay, So now we will claim that, or we will prove that Tn is also eigenvalue. Okay, so sorry, Vn. So so Vn is also eigenvalue. But what is T of Bn? So T of Bn, because this is T has upper triangular form, so you can write down this is kind of, I think, a one, the last one, so a1 n with b1 plus a2n into b2 and so on, right? And last one will be what? So okay, so a1 1 a2 2 and then a n vn, last one. Okay, sorry, small a n. Okay, so this is that upper triangular forms that coming from Schur's theorem. And now we need to prove that we need to check that these a1 n a2 n, these are all 0. If I prove these all are 0, then only the last part will be remaining. Okay, now what is say for example a, say, j of n for any j. So for j equal to 1 to up to n minus 1, I am choosing this. Now a in j's is what? So you remember that this you can represent as inner product of t of vn with vj, right? But t of vn vj is nothing but vn times t star of vj, right? Vn times t star of vj. And okay, so I need to prove one theorem probably that I missed. Maybe I will give you proof that for normal operator, if you have eigenvalue which is, so if you have eigenvalue of t, then that the conjugate of that will be eigenvalue of t star. So this will be something like Vn of Cj bar of Vj, but then that Cj bar will comes outside, so that will be Vn Vj, whatever. So that I will give the proof, but remember that t star also have eigenvalue, and that will be the Cj. But maybe in this case, normally tells you that the bar of the original one. Okay, but anyway, what is the important thing is that this is orthonormal, right? So this becomes 0 actually. This is important thing. So whenever your this j is less than n, this always vanishes, right? So what does that mean? That means this person vanishes, this person vanishes, till a n minus 1 of n is vanishes, right? So that's what you'll have. So you'll have t of vn, the nth vector will be a n into vn. So what does that mean? That means vn is also an eigenvector of t, and this is the proof. So this is index hypothesis. So till you choose till n minus 1, which is true, and then you show that in the nth position also true, and that tells you that on a complex inner product space, a operator is linear normal if and only we have a orthonormal basis which consists of eigenvectors of t. Okay, so this is kind of the version of diagonal derivative, right? That b basis consists of eigenvectors of this eigenvectors of t, right? Okay, so maybe I will stop here today.